The last time we talked about the structure of a linked list. Today and Friday we're going to reinforce that content and just talk about more of the implications and just get more practice with the linked list. But we do have homework 3 out. So for those of you who aren't too, what's the right word? I want to say hungover. I'll just stick with that. Aren't too hungover on the homework 2 deadlines that just passed and are ready for homework 3. You do have everything that you need right now to complete task 1. And then today and Friday, we're going to reinforce linked lists so you just have more background and be more comfortable with the task 1 content. But right now, just knowing the structure of a linked list, that it has its value and a reference to the next node, that's all you need to know to get through task 1. There are 3 methods to write. 2 of them take the linked list node that we created in class as a parameter, a reference to the head of a linked list, and the last one returns a linked list. So you'll be creating your own linked list using that linked list node class and then returning that linked list. That's all stuff that you can do. Let me rephrase that. That's all stuff that you know the concepts of from Monday's lecture. So you have all the background knowledge, all the conceptual knowledge that you need to be able to do that. And then, of course, coding it up is going to take practice and time and studying and all that good stuff. But you have the background from lecture to be able to do that. Today I want to talk more about linked lists, specifically stacks and queues. And we're going to go into a small memory diagram to reinforce your understanding of linked lists and just get more comfortable with them. I feel like I said that 3 times already now, though. Let's frickin' do it. Any questions before we get into it? When will the questions in Autolab be graded? I can't give you a definitive answer. I manually process them, which I think 4 lecture questions behind right now. Either 4 or 7 even. I forget how far behind I am right now. I meant to do them yesterday, but then I ran out of time. It was 2 in the morning, and I just wanted to sleep. So either tonight or tomorrow, I'll likely catch up on all of them. But suffice to know, I don't put this at too high of a priority because I think the lecture questions have been quite straightforward recently. You know that you will get the points coming your way. The points are going to be there eventually. And I don't think there have been any too tricky questions where you're really dying to know, did I get that one right? I do want to get them up there because the confirmation is nice to know that you got those points, 100%, that nothing weird happened with the submission or anything like that. So I do want to get them up there. But processing task submissions and helping students out getting the tasks done, I do prioritize that higher because that is, more do or die, more stressful. Especially with the deadlines this morning. I'll process the deadline extensions, the recovery opportunity usages. I'll definitely do that before processing the lecture questions, is what I mean by that. Any other questions? Do it. Stacks and queues. So with stacks and queues, I'll say right off the bat, I have kind of hot take on stacks and queues is the concept of a stack, the concept of a queue are very important. They're fundamental computer science topics that you pretty much just have to know. They're so fundamental that you're expected to know them. When you have job interviews, these are questions that interviewers like to come up with, things about stacks and queues. It's just something you have to know. I have to cover them. But the actual data structures themselves, the implementations that we're going to see of these data structures, I'm not a fan of. I don't like them. I'll explain why throughout the lecture. I'll keep bringing it up again. But I don't like them specifically because they are built on linked lists, but they restrict the functionality of a linked list. So the stack that we'll see, we're going to have this wrapper class around a linked list that just hides a lot of the functionality of a linked list from you. And I don't know, I don't like that. I don't like it at all. My counterpoint to that is just use a list. Just use a linked list. You don't have to artificially restrict your functionality with these data structures. The concepts are awesome. They're amazing. You need to know them. But the actual data structures themselves, since all they do is take power away from you, I just can't recommend them. I just don't like them. Just use a list. And I'll show you exactly what I mean by that as we move through this lecture. So a stack, we've seen a stack throughout this whole semester. The memory stack is a stack data structure. A stack is a last in, first out data structure. So whatever the last element you added to this data structure is the only element that you can remove from the data structure. You can think of this as a physical stack. We have a stack of folders. The only things you can do with this stack is add a new folder to the top and remove the top folder. Now, physically, you could pick up the whole stack, or you could finagle your way to get the middle of the stack, sure. But the stack data structure says the only folder you're able to access is the top one, and the only way you can add to the stack is adding to the top. Those are the only two things you can do. And that's it. That's a stack. Two things that you can do. Add to the top, remove from the top. We saw this in our stack memory. You can only add a stack frame to the top of the stack, and the top stack frame, or the bottom visually in our memory diagrams, the stack frame on the top of the stack is the only one that's active. You can't access the second to last stack frame. You're just not allowed to do it. You can't access any of its variables. Can't happen. You can add a new stack frame to the top of the stack and make that the new top, and you can remove the current stack frame by returning a value and getting rid of that stack frame. But it very much follows the concept of a stack data structure. So the stack data structure, you can only modify the top. We have two methods. Push is when we add an element to the top, and pop, we remove the top element. That's it. Some implementations of a stack, in some languages you'll see a third method, either top or peek, which will return a reference to the top element without removing it from the stack. It's not required for the concept of a stack, but sometimes you will see that out there. This is all that's required for a stack. This is all we'll talk about today. Push and pop will remove the top element and return a reference to it. So if you even want to know what the top element is, you have to pop it off of the stack and then get that reference and then work with it there. And if you really wanted to just look at it, just pop it back onto the stack. It's no big deal. And here's how that looks in code. So we're going to create a stack class. It's going to take this type parameter A and forward that type parameter to our linked list, our underlying list. It's going to store a linked list, a reference to the top of the stack, as a state variable. So it's a wrapper class around a linked list that just hides a lot of the functionality. It will only expose two methods, push and pop. Push is going to take an element of the type parameter, matching the type of the type parameter, and prepend to the linked list. We're going to replace the reference top to a new linked list node containing the element that we're adding and a reference to the old top of the list. So if we're pushing the very first element to this list, top is going to be null, and this dot top, this will be null. We'll get a linked list node referring to null with the value A, and we're going to set that as the reference to the top. So we're going to have a reference to top, which is one linked list node referring to null, containing the one element in the stack. And then as we add more elements, it's just the prepend operator that we saw before. So we're prepending to the front of the linked list when we're pushing to the stack. Pop, we're going to do the exact opposite. We're going to remove the very first element from the list. So we want to capture that value. That's what we're going to return, whatever the value is at the front of the list. And then we're going to update top to be a reference to top.next, which is the previous second element of the stack, or the second element of the linked list. We're going to update that reference to refer to that second element, and then that effectively removes the first element from the linked list. So this is how we can implement push and pop. It's prepend and remove the first element by reference. For what it's worth, if you call pop on an empty stack, you're going to get a null pointer exception with this code. It's common for stack data structures, any implementation I've seen of a stack. If you try to pop from an empty stack, it will throw an exception, it'll crash your program. You're not allowed to do it. It won't always I'm just using a raw null pointer exception. Usually it'll be like a pop from an empty stack exception, some custom exception, but it will crash. So mine is no exception. The reason for that is this dot top, when we have an empty stack, this dot top is null. Now null means there should be a reference here, but we don't have any reference. There's just no reference there. It's null. It's empty. It's no reference. And then we're trying to access the object. The dot operator is going to access the object referred to by that reference. So we have null, and we're trying to access the object referred to by the reference. Well, there is no object referred to by null. It's the lack of a reference. So as soon as we hit this dot right here, we get a null pointer exception, program crashes. You might see this if you have, now that we're working with nulls, this is the first time we see null in our code. If you do try to access the reference referred to by null, you'll see that null pointer exception. That's what's happening, is you're trying to access the object referred to by null. You might see this. The last lecture, I'm like, you won't really see this in Scala, but then after lecture, somebody came up to me with the null pointer exception in their code. So part of the reason why I was late, too, trying to find the null pointer exception. But so you might see that on this last homework, but where you're definitely going to see null pointer exceptions in seg faults is in 220 next semester, if you're going on to 220 right away. Some students like to split, I say that, some students like to split up 220 and 250. I didn't mean anything bad by that, but some students will take just 250 and then just 220. So if you are taking 220 next semester, you'll see a lot of null pointer exceptions in C, because C just messes around with null a lot more than we do. Since I mentioned it, I'll go in a little in depth on this one. You also see seg faults or segmentation fault. Seg fault is just short for segmentation fault. That means you tried to access memory that you don't have control of. So we have certain sections of memory when we ask for memory on the heap and we have our stack memory. We're confined to those memory addresses. And Scala really doesn't let us violate that at all. The JVM specifically doesn't let us violate the way we access memory. You can. It's tricky to do, though. You're really not going to run into seg faults in Scala or Java or any JVM-based language. In C, you will. I guarantee you. If you make it through all of 220 without seeing a single seg fault, you need to come see me because I want to give you an award, and I don't know. I don't know what I do. I'd be absolutely amazed if you made through all of 220 without a single seg fault. But in C, you're able to access memory that you shouldn't be able to access, and then the operating system's going to shut you down and be like, hey, what are you doing? You can't access that, and then shut down your program. So those are two types of errors you're definitely going to see in 220. But yeah, this implementation, popping from an empty stack, null pointer exception. Our usage of a stack, we're going to call push and pop. So we have a new stack of the type parameter. I'm going to push 3, 7, 2, negative 5. So at this point, the stack is 3, 7, 2, negative 5. And we're going to pop negative 5 off of the stack. So the resulting stack is going to be 3, 7, 2. And negative 5 was popped off, and element will be negative 5. This is the same exact usage of Scala's built-in stack. So if you import Scala's stack or if you import the stack from the examples repo, it's the exact same usage. This code will compile and run with either of those imports. It's the same exact usage, same exact method name, same exact behavior. But of course, I recommend not using those because when you import stack, you just get push and pop. That's all you can do. So say you're coding, you import stack, and you have a use case where you need the stack data structure. You're only going to mess with the top of the stack. You're going to push and pop from the top. That's the use case that you have. And then at some point while you're coding, you say, boy, I'd really like to know the size of the stack. Can't do it. Push and pop, that's it. Size isn't included in there. You can't ask a stack for its size. So that's why I recommend just using a list and applying the concept of a stack and leaving your options open, because now you can always just ask this list for its size, and you don't have that issue. If you're using a stack, you've got to rewrite your whole code to not use a stack anymore and then ask it for its size. The reason for this, stack and queue are designed to make sure you're going to be efficient. Push and pop and the queue methods that we're going to see are all O of 1 operations, constant time operations. So if I have a stack of 5 elements or if I have a stack of 5 billion elements, push and pop are going to have the same runtime. They're both going to be very fast all the time. Size is an O of n operation. You have to navigate the entire linked list to get what its size is. Very slow operation. So stack just says, no, we're not allowing any slow operations. We're only allowing these 2 very efficient operations, push and pop, and that's it. That's all you get. So the advantage of using the stack data structure in your code and not the concept of a stack like I have on screen right now, using a raw linked list, the advantage would be if the advantage would be that you're restricted to only using the efficient methods, so you can't accidentally use something that's inefficient and slow down your code. I say just be a knowledgeable programmer and just don't do the inefficient things. That's, I think, a much better approach. Just be aware of what a linked list is, how it works, and only use the efficient things. But then when you need some information like size that's inefficient, just be mindful that that is going to be O of n. Don't start calling it constantly, but have that functionality available to you. But this is how we would use a list. This is what I would recommend if you need a stack. Use Scala's list. Prepend the way we've been prepending all semester. And to pop, stack.tail, or in a few slides I'll switch that to drop 1. These both do the same thing. Scala's built-in list uses tail instead of next, but stack.tail here is the same as our stack.next. Next in our linked list node. I don't know why they use tail. I think it's a little confusing. I would much prefer next. Tail makes me think of the last element of the entire list, not the next element. Like tail doesn't make sense to be the second element of lists, at least not to me. It doesn't seem too intuitive. But that's what Scala calls it. Tail is a reference to the next element from any element. And this is going to pop. So this is the same exact functionality, same behavior that we saw with the stack class, but built with a Scala list. And this is my favorite deprecation warning that I've ever seen. I already formed my opinions of stack before I saw this, but then I saw this and saw that the Scala developers actually agree with me. So this is Scala's built-in stack class. This is the actual source code for Scala. The developers left a note for us saying, don't use this. Why the hell are you using this? Don't do it. It says exactly what I recommend of don't even bother using this data structure. It's probably slow. It's not elegant at all. Just use a list and use prepend and tail. And that's it. Like, don't bother with this data structure. So they wrote the data structure because people probably expected them to have a stack data structure, but they actually tell people right up front, like, don't actually use this. Why? Why are you using this? Just use a list and keep your options open. But this should be inefficient, right? I've been saying all semester that when you modify a list, you don't actually modify the list at all. What you're doing is creating a brand new list with those changes applied. So 3 prepend stack doesn't modify this list in any way. It creates a brand new list containing 3 and then all of the elements of the original list. For 3, it's, there was an empty list. But by the time we get to -5, we're prepending -5 to this list of 2, 7, 3, creating a brand new list with 4 elements, and then returning a reference to that list containing 4 elements, and then we have to reassign it to our variable in order to see that change. This is because Scala's list is immutable, meaning that all of the values and references that they call tail, but we call next, they're all vals. They can't change. The list can't change at all. So isn't this really inefficient to do this? And I mentioned this on Monday, but I want to hammer this point home today of why this is not inefficient. What does it mean for something as a wrapper class? So I'm saying stack is a wrapper class for the linked list node because it has a linked list node as a state variable, and then it has its functionality that it adds to that, which really kind of just removes a lot of functionality. But you're accessing a linked list. When you create a new stack, you're actually accessing a linked list. It's using a linked list, but it's building a new interface to be able to interact with that linked list. So instead of interacting with the linked list directly, this wrapper class says, no, you use my methods, and then I'll talk to the linked list for you. So we say that's a wrapper class for the linked list class. I'm trying to think of another example where we've seen that. I don't know if we have seen that before. We'll explain stack equals stack.tail. So .tails in Scala's built-in list is the same as .next in our linked list node. So we're updating the reference to the stack, which is now a reference to the node -5. We're updating that to a reference to the node containing 2. Brand, that's not right. Second element, not the last element. Ren's an alum, by the way, if anybody's wondering. They're not in the room. All right. So why isn't this horribly, horribly inefficient? Let's talk about this. So when we prepend to a stack, specifically when we're prepending -5 in this example, what's in the red box is our original list. That's our list before we prepend -5, and then our whole list, that's our list after prepending -5. So when we prepend -5, and this is what the Scala list does, by the way. It does the same thing as our linked list node, just with some stranger syntax. We're creating a brand new linked list node with the value -5, and we're creating its next variable, or tail in Scala. Its next variable is going to refer to the node containing the value 2, or the head of the old linked list. So I created this node, gave it the value we're prepending, and had its next refer to this node, the head of the linked list. So what happened to the original list that's in the red box? Nothing. Nothing changed. Absolutely nothing changed with the original list. So even though this is a val, this is a val, 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 we didn't violate any of those vals. We didn't reassign anything. We didn't change anything. Nothing changed at all. So if somebody had a reference to this node, either before or after we prepended -5, they still have a linked list, a reference to a linked list containing 273. We didn't change anything that they're doing. We didn't violate immutability. We didn't violate the vals. We didn't do anything. We just created our own thing and said, hey, have this refer to that other list. But we didn't change anything about this list. So we did, in fact, create a brand new linked list of size 4, but we're reusing the linked list of size 3. We're reusing all of that memory. We're not getting rid of it. We're not copying anything. We're just referring to the old list. So each time we prepend, like we had the empty list, We had a list of size 1. We prepended 7 to it. Each time we prepended 2, we prepended -5. Every time we prepended, we didn't modify anything with the old list. So technically, there's 4 lists in memory, but we only needed 4 nodes to be able to do that. And we're just reusing the old lists and prepending by taking advantage of references to be able to get our bigger and bigger lists. So when we prepend -5, we do return a reference to a brand new list containing all 4 elements, but it's just a reference to this node instead of a reference to this node. And everything else gets reused. But this is why we have to reassign our stack. Stack has to be reassigned because this is creating, underneath the hood, this is calling a constructor and doing all that goodness that we do in our code. Scala syntax hides all that from us. But we're creating a brand new node with -5 and next pointing to this one, and then we're updating stack to refer to this node instead of this node. The original list didn't change. Beautiful thing. Very efficient. Very fast. Same thing with popping. And instead of .tail or .next, I did drop 1 here. Drop 1 is going to return a reference to a node that's this many nodes down the list. It's a weird way of wording that. But so drop 1 is going to start at this node. Stack is this node right now. Drop 1 is going to return a reference after going 1 hop down this list. So we go 1 hop and then return a reference to this node. If we did drop of 3, we'd go 3 hops. 1, 2, 3, and return a reference to this node. So if I drop 1, again, I'm not modifying my list at all. I'm just returning a reference to a different location in that list and then updating my reference stored in stack. Effectively, from the stack variables perspective, we just removed an element from this list, but all we did was replace the reference stored in stack. We didn't change anything at all in memory. We just changed stack to refer to a different node. We replaced 1 reference. It's about as efficient as we could possibly get. We just swapped out 1 reference for another. We didn't ask for any extra heap space. We didn't remove any heap space. We didn't change anything in memory except the value stored in 1 variable in stack memory. We didn't even declare a new variable or anything. Super efficient, very, very efficient. And again, didn't change anything in the red box. Didn't change anything with this list because we didn't change anything in memory at all. All right, Q, very similar data structure conceptually, but we're going to see quite a few changes when we start analyzing this thing. So Q is our first in, first out data structure. The first one to get into the queue is the first one out. This is our typical line. You're waiting in line somewhere. You enter the back of the line, and you have to wait till you get all the way up to the front of the line before you can get whatever you were waiting for. We're going to do this with 2 methods, just like our stack, except they're going to be called NQ and DQ. You can NQ into the end of the line, or the queue, and you can DQ from the front of the queue. And that's it. You get 2 operations. You can't ask it for its size. You can't print a queue to the screen. You can't, well, you can, but you're probably going to get a reference. You can just because it's of any type in Scala. Conceptually, you can't. In Scala's implementation, you can. I don't know what a Scala queue would print out. Probably nothing meaningful. But NQ and DQ, that's all we get. The code gets a little bit more complex, but mostly just because we have some extra bookkeeping, because we have to work at both ends of the linked list. So we need a reference to the front or the head of the linked list and the last element in the linked list. We need references to both those nodes to be able to push NQ from one end and DQ from the other end. I'm going to NQ at the back of the linked list and DQ from the front, for what it's worth. I could do it the other way around. It's not going to change much about how I talk about it. It's just the way I ended up coding this one. So when we NQ, I'm going to check if the back is null. If the back is null, I know I'm NQing into an empty queue, and I have to be mindful of my front reference, because the front and back are both referring to null. So I'm going to create a new node referring to null, a linked list of size 1, and front and back are both referring to that same element. There's only one element. the last and first person in line is the same person. It's just one element. If back is not null, I'm enqueuing into a non-empty list. I'm going to create a new linked list node referring to null. That's going to be the new end of my list. And I'm going to update back's next to refer to that new node. So the back, instead of referring to null, is going to refer to the new node that I've created, and then update the reference back to refer to that new node that I just created, which is the new end of the line, end of the linked list. This is our append operation. So I'm appending to the end of the linked list to enqueue. And then for dequeue, I'm going to do the same thing we did with a stack. I'm going to get the value at the front and return it, and then update the reference of front to the second element. What was the second element in the queue, or the second person in line, is now the first person in line. And then a little extra bookkeeping. If front is null, so if I just dequeued the only element, if this was a queue of size 1, then I'm going to update back also to null. Front will be null. That means back is null also. So I avoid back being a reference to a node containing an element that's been dequeued. I don't want to, I just need to keep track of that. So I have a couple lines of code to keep track of that. And this will also give me a null pointer exception. If I dequeue from an empty queue in this code, I'm going to get a null pointer exception. Which is pretty standard. You're not necessarily null pointer, but again, you'll get some form of error. If you create a Scala queue, just say new queue, queue.dequeue, you'll get an error and your program will crash. It's probably dequeue from an empty queue is probably the error that it'll tell you. The usage, none too fancy here. We're going to call enqueue and dequeue. So we're going to enqueue. This will give us a queue with 3, 7, 2, negative 5. And then we dequeue 3 and end up with 7, 2, negative 5 as our queue after this code runs. This is the same usage as Scala's built-in queue, if you want to use that queue. If you want to use a queue at all, I should say. It was asked in the other lecture. You don't need stacks or queues for Objective 1. You don't necessarily need these data structures at all, like I said before. But when you use your list, using them as either a stack or a queue, being mindful of these concepts can be helpful, especially for task 3. We'll want to use a queue when we start working with graphs. And you'll see that when we get there. That'll be our first real application of a queue. It's hard to write questions that really funnel you into stacks and queues. But I need to show you the concepts anyway. Scala's built-in queue is built on a mutable list. So Scala's list class that we've been using all semester, Scala's queue is not built on that list. It's built on a mutable version of that, just like our linked list node class. And I want to talk about why that is. So there's no efficient way to use an immutable list to build a queue. The reason is that you have to work on both ends of this list. With a stack, we just worked with the front of the list. We prepended and we removed from the front. We can do those very efficiently just by manipulating references. But when we enqueued in our case, and if I flip this around and enqueued, I could enqueue with prepend and get rid of this issue we're about to talk about, but then I'll have the same issue when we dequeue. So when we work at the end of the linked list, here we're appending to the linked list to enqueue an element. What's in the red box was the original queue, and I'm enqueuing the value 3. When I enqueue 3, I create a new node, refers to null, but I also had to go to this value next of the previous end of the queue and update that to be a reference to the new node that I just created. And this is our problem with enqueuing, and this is our problem with appending to linked lists in general, to an immutable linked list, is that we did have to modify the list. We did have to modify our original list. So if that next variable is a val, we can't do this. Can't be done. You can't append to an immutable list efficiently. So when you append to a Scala's list, when you have a Scala list, you say, give me a list, and then you append to it. What actually happens is it has to copy that entire list into new locations in memory and then do the append and return a reference to that brand new list. So where prepend, we could take advantage of references and reuse the entire original list, we can't do that with append. So I mentioned this earlier in the semester, append slow, prepend fast. This is why. When you append to an immutable list, you do have to modify the original list. So in Scala's immutable list, you have this list of size 3 and you want to append to it. It's going to have to copy all these elements and add the fourth node. So what you'll end up with is a total of 7 nodes in memory. You have to allocate space for 4 more nodes to be able to append an element. With 4, not so bad. If it's 1,000,000, you're feeling this. You're feeling the pain. You've got to copy 1,000,000 nodes, create 1,000,000 new linked list nodes to add your 1,000,001st element. That's painful. And you can actually see this. You can feel the pain yourself. Go to your homework 1 code and just build some list. Use a Scala list. Go through that cities.csv and just take any information from each city and build a list out of it. There's about 130,000 cities in that file. So you have a list of size 130,000-ish. Bless you. And write your code using prepend and then rewrite it using append. You'll be able to feel the difference. Append is horrifically slow when using immutable lists. You'll end up using tons of memory to be able to get all those lists in memory. And this is why Scala's built-in queue uses an immutable list. There's no real good way to get around this. You either use an immutable list or you eat all that inefficiency. And since the point of a queue and stack is to restrict you to only efficient O of 1 constant time operations, there would be no point in using an immutable list for a queue because it completely blows up the purpose of a queue. So we use mutable lists. Yeah. Okay. I'm glad you asked, but I was watching the clock. I'm like, maybe no one will ask in this lecture. They asked in the other lecture, so I'll try to keep it more brief than I did in the last one. So the question is, why are we fucking around with immutable lists? Like, why? Why even bother? Just use immutable everything. Use mutable everything. Why mess around with immutable? So immutability is gaining a lot more popularity now because we have a lot more concurrent programs. We're moving to more multi-core, multi-processor even machines and even distributed systems where we have multiple machines all supporting the same app. So when you have multiple processes, not necessarily multiple processes, but when you have multiple pieces of code running concurrently and they're both accessing the same data structure, if one of them is changing that data structure while the other one is iterating over it, we're just asking for bugs. We're going to run into issues with that. So when we move to concurrency and distributed systems, as we move to this world, which is just the reality now, with processors aren't getting faster anymore, we're just getting more cores and more stuff happening concurrently. As we do that, we need to be mindful of the shared data. So immutability says, okay, let's just not let anybody change the data. If they change it, like this linked list, if they're prepending, it's not affecting any other code that might be accessing that data. Like if somebody's in queuing at the same time where somebody else is iterating over a list, somebody else appended or prepended to it, that's going to cause some problems. So immutability just says, let's solve that. You can't change anything. Problem solved. There are other approaches, the other ways to get rid of these issues, but immutability is gaining more and more popularity as just the be-all solution to this problem. And it is just a reality. You will be writing concurrent code. We actually used to teach concurrency in 116, but it was just too much too soon. Second semester is a bit too early for that. But you will be writing concurrent code. A lot of you will probably be writing distributed systems, distributed programs as well. These are things that we have to be mindful of. And immutability just solves all your problems. It's immutable. Don't worry about it. You don't have to worry about two things modifying the same data structure at the same time because they can't change it. I think I can still get through the memory diagram. That was just 3 minutes. It was a fine explanation. Any follow-up questions on that? Okay. Because the problem is I want to talk about that for a long time because it's interesting. But we do got to get through the memory diagram too. If I'm missing anything here. Yeah, if you had a mutable doubly linked list, that would be it would be easier to implement that queue, right? Did I say that right? There's more things you can do with a doubly linked list where each node doesn't just know its next, but it knows its previous. But with a doubly linked list, you have no chance of immutability at all because you have to modify those references whether you're prepending or appending. So if you're looking for immutability, singly linked is the way to go. But you'll learn about doubly linked lists in 250. There's a lot more fun algorithms that you can do with them. Okay, so let's do this memory diagram in 5-ish minutes. Not too much going on here. I don't have a whole lot to talk about. This first chunk we've already seen. So I'm going to skip it. We did the building of the linked list last time. We're prepending. So we have a reference to a linked list node, which has the value 5. Its next has the value 3. Its next has the value 1. Its next is null, so it's the end of the list. So we have the list 5, 3, 1 in memory stored at myList. Then we're going to work with this a little bit. We have this line here, mylist.next.next.value. Parsing through this, if you just have the code, parsing through this and figuring out what value that's going to be can be a bit tricky. It's hard to follow all this. But with the memory diagram, it's pretty trivial. Just remember, whenever you have a dot, you're following the reference. You have a reference, and you're following it to the object it refers to. So mylist, dot, next, dot, next, dot, value, 1. Just follow the references each time you see a dot. Print 1 to the screen. Now it's time for some recursion. Now I rewrote this when we saw size on Monday. I wrote this a slightly different way. This time I rewrote it as tail recursion. Tail recursion is something I get asked about a bit. If you don't care about tail recursion, you will get through this course without knowing it. But for those of you interested in this, I just want to sneak it into one example. One example here. So tail recursion is where the recursive call is the last thing that a method does. Our old size method would make a recursive call, and then when that recursive call returns, we would add 1 to it. So it had some work to do after the recursive call. With tail recursion, the recursive call is the last thing, and we're just returning whatever the recursive call returns. So I had to modify the code a little bit to do this. I still want size taking no parameters to be my API. This is my interface of how people interact with my code. When you ask a list for its size, this is how you expect to call it, just dot size with no parameters. But for my recursion, I want it to take a parameter, but I don't want to expose that to whoever's calling this method. So I'm going to have size with no parameters, call my size recursion, which we often call a helper method. We're going to call the recursion helper method with a default parameter and then start the recursion. With this tail recursion setup to get rid of, to make that recursive call the last call, I'm going to have the accumulation of these plus 1s happen as we go down the recursion instead of as we go up the recursion. And then in the base case is going to compute the final answer and then just return that all the way up the recursion. The advantage to this is the JVM can then collapse all your stack frames into one stack frame and get you a lot more efficiency. In our memory diagrams, even if we give you tail recursion, something that's technically tail recursive on the quiz, you're still drawing all of your stack frames, and I'll draw my stack frames here. We're not concerned with a compiler JVM optimization in our memory diagrams. All right, so with that, we're going to call size. Size is going to defer to the helper method, and we're going to call this with size 1. We have mylist.size, mylist 480, so 480 is this. We're calling this from the same method. I could do this dot tail size tail rec here. I didn't put my this dot. I probably should every single time. But that called size tail rec from the same object. So we still have 480, and then size is seated at 0. And then we're going to go through the recursion. This dot next is not null. This dot next is not null. So we're going to go to the else, which we're going to go to this dot next dot size tail rec with size plus 1. So at 200, we get size of 1. Next is not null. Make another recursive call with this dot next. Put another frame on the stack. This, do our check. This dot next is null, so we've hit the base case, and we're going to compute size plus 1. So size plus 1, we have 2. We're going to bump that up by 1, and then return 3 all the way up this recursion. When we have recursive calls, our return arrow goes right to the previous stack frame, and we're going to return this all the way up. All these stack frames are just sitting there waiting for either this method call to return, and it's going to return whatever that returned, or for this call to return, and it'll return whatever that returns. So this 3 is going to be returned from the base case all the way up to the main stack frame. And what the JVM will do is recognize that these two stack frames were just sitting there waiting to get a return value so it can return the return value. So what the JVM does is say, we don't need those two stack frames. It reuses that space in the stack and actually won't keep these stack frames on the stack. Each recursive call reuses the same stack frame. Again, in your memory diagrams, don't skip your stack frames, draw them all out. But that's an optimization that you would get using tail recursion. It's why you would want to use tail recursion. It saves memory and can avoid stack overflow errors. Where you would have a stack overflow, if you're using tail recursion, you don't get a stack overflow. All right, and have a great day. I'll see you all Friday.